In my previous video, we introduced common classification algorithms. Now let's dive into the other category of supervised learning, which is regression, where the output variable is continuous and numeric. We will walk through how to implement and compare different types of regression models, linear regression, polynomial regression, and two regressions with regularization techniques, Lasso and Ridge. Linear regression finds the optimal linear relationship between independent variables and dependent variables, then makes prediction accordingly. The simplest form is y equals b0 plus b1x. When there is only one input feature, linear regression model fits the line in a two-dimensional space. This line will attempt to minimize the residuals between predicted values and actual values. A common cost function to measure the magnitude of residuals is residual sum of squared, or RSS. It takes the sum of square value of the difference between all actual and predicted values. As more features are introduced, simple linear regression evolves into multiple linear regression. Polynomial regression is a variation of linear regression transformed by polynomial features. It adds interactions between independent variables. For example, if polynomial effect with degree of 2 is applied, if the original input features x1, x2, x3, will expands to x1 x1, x1 x2, x1 x3, etc., which creates the association between features. As the result, the relationship is no longer linear, instead provide a nonlinear fit to the data. Now let's talk about regression models with regularization. Lasso regression is a variation of linear regression with L1 regularization. Simply put, it adds an extra element to the residuals RSS that regression models are trying to minimize. It is called L1 regularization because this added regularization term is proportional to the absolute value of coefficient b1 with the degree of 1. The regularization term here is based on the simplest linear regression form y equals b0 plus b1x. Compared to ridge regression, it is better at bringing the coefficients of some features to 0, hence a suitable technique for feature elimination. You'll see in the later section when we discuss feature importance. Ridge regression is the other regression variation with L2 regularization. So not hard to infer that the regularization term is based on the squared value of coefficients with the degree of 2. Compared to lasso regression, ridge regression has the advantage of faster convergence and less computation cost. The regularization strength of lasso and ridge is determined by lambda value. Larger lambda values shrink down the coefficients, which makes the model more flattened and with less variance. Therefore, regularization techniques are commonly used for preventing model overfitting. Now let's put this into practice. Check out code snippet link in the description if you are interested in getting the full code of this project. Kaggle dataset World Happiness Report is used as an example. Here are the useful exploratory data analysis and feature engineering techniques that are suitable for regression models. Apply histogram to understand the distribution of each features. As shown below, social support appears to be heavily left-skewed, whereas generosity and perceptions of corruption are right-skewed. We can also combine the histogram with the skew function to quantify if feature is heavily left or right-skewed. For example, social support has the skewness of -1.13 and generosity has the skewness of 0.74. This also indicates that feature engineering techniques are required to transform them to more normally distributed shape. There are several feature engineering techniques to transform skewed data into more normally distributed shape. For example, log transformation and square root transformation. Since regularization techniques are manipulating the coefficients value, this makes the model performance sensitive to the scale of features. So features should also be transformed to the same scale before feeding into the model. There are several built-in scalars in Python, such as standard scalar, min-max scalar, and robust scalar. As you can see, scalars won't affect the distribution and shape of the data, but will change the range of the data. After bringing all the features into the same scale, Seaborn pair plot can be used to visualize the correlation between pair features. The scatter plots suggest that GDP per capita, social support, healthy life expectancy tend to form a linear relationship with target variable score, so may have higher coefficient values. Let's find out if that's the case when we are examining the feature importance. Now let's build 3 regression models, linear regression, ridge regression and lasso regression using Python, and compare their performance. Firstly, visualize the predicted values against actual values of 3 models in one scatter plot, which suggests that their predictions mostly overlapped with each other under current parameter settings. The second step is to experiment how different lambda values, which is alpha in the scikit-learn library, affect the models. Specifically, how feature importance and coefficient values change as alpha value increased from 0.0001 to 1. Based on coefficients values generated from both lasso and ridge models, GDP per capita, social support, healthy life expectancy appear to be the top 3 highest importance features. This is aligned with the findings from previous scatter plots, suggesting that they are the main drivers of country happy score. The side-by-side comparison also indicates that the increase in alpha values impact lasso and ridge at different level. Features in lasso are more strongly suppressed. That's why lasso is often chosen for the purpose of feature selection. Last step, evaluate the performance of lasso regression and ridge regression model performance, before and after polynomial effect, when alpha value changes. Here I used MSE, mean squared error, to evaluate model performance. It is the mean of residual sum of squared we discussed earlier. By plotting ridge versus lasso side by side, we can tell that polynomial, which is the yellow line, decreases MSE in general, so enhance model performance. This effect is more significant in ridge regression when alpha increases to 1, and more significant in lasso regression when alpha is closer to 0.0001. By comparing baseline linear regression and polynomial regression side by side, it indicates that they have lasso and ridge have similar accuracy when alpha values are low, but lasso significantly deteriorates when alpha is closer to 1. Same pattern is observed with and without polynomial transformation. However, even if polynomial transformation improves the performance of regression models, it makes the model interpretability more difficult. It is hard to tell the main model drivers from a polynomial regression. Less error does not always guarantee a better model, and it is about to find the right balance between predictability and interpretability based on the project objectives. Thanks for watching. If you find this video helpful, please like and subscribe. Look forward to see you in the next one.